Hi everyone, so here we're gonna talk about things about springs or simple harmonic oscillation. So basically the setup you'll have usually is you have some mass that's attached to a spring, that's attached to a wall that doesn't move, and it's all on this frictionless surface. Usually we'll also define the rest position, so that's where the spring isn't stretched or contracted, to be x equals 0. So x equals 0 just right here in the middle of the mass. And so you learned a lot about different quantities when it comes to simple harmonic motion. First there's the mass, which usually you'll know. And then there's the spring constant, there's period, frequency, angular frequency, there's the mechanical energy of the system, there's potential energy, kinetic energy, it can have a velocity when it's moving, there's an amplitude, and you have all of these quantities. So it turns out that they're actually related in some really simple ways. And so that's what we'll talk about here. So if you know the mass of the system, then all you need to know is you need to know one of these, and you could find the rest of them, and then you just need to know one of these, and you can figure out the rest of these. So really, you just need the mass and two other things in order to know everything about one of these simple harmonic oscillator problems. So how are these all related to each other? Well, we learned in class that the angular frequency is equal to the square root of k over m. That's the spring constant that's specific to the spring over the mass that is attached to the spring. So basically all this means is that if k is bigger, that means you got like a stronger spring. It's much stronger. And so if you move the mass, then what'll happen is it'll start to oscillate back and forth, but if it's a stronger spring, it'll go faster and faster. So that means the frequency is bigger because the spring constant is bigger. The spring is just stronger. And then if the mass is bigger, if it just weighs more, the spring's going to have a harder time, so it's going to move more slowly back and forth. So the angular frequency will be lower because it's slower. The frequency, faster means bigger. And then the angular frequency is, since angular frequency is, as you learned, theta over theta per second, that's number of radians per second, to get to frequency, which is rotations or revolutions per second, is just 2 pi times, so we have 2 pi times the frequency, because there's 2 pi radians in one revolution. And then period is just 1 over frequency. This is equal to 2 pi over period. So basically you could use the equality of any of these, like this is equal to that, this is equal to that, to figure out, if you know one of them, you could figure out basically the rest of them. And so that's how all the frequencies and periods and the spring constant are related. Okay, so now let's move to energy. Okay, so let's say you know, for example, the amplitude. You know amplitude. And so what that means is that, you know that this thing can be written as A sine omega t. That's the position as a function of time. So that's just something on the side here. But so if you know this amplitude, basically what that means is that A is actually the position when this mass goes the furthest it can go. So the spring stretches and the mass goes over here, and then A is going to be the position from x equals 0 to its furthest point here. And then right here it'll start turning around and going back because of the restoring force. So the way that we can relate this to energy is we can find that the total mechanical energy, E mechanical, at this point, just the turning point, so I'll call this turning. So the mechanical energy at this turning point is just going to be potential at the turning point because it's not moving, it's just turning around. And we know that the potential energy is just 1/2 k x squared, but here x is equal to a. So it's 1/2 k a squared. And so now we know that since the total mechanical energy doesn't change, and we know it at one point, then we'll know the mechanical energy the whole time, and it relates to the amplitude like this. Okay, so how do we figure out, say, the kinetic energy at some other point? Well, now you know E mechanical, so E mechanical, which is equal to U plus K, is equal to, well, you know expressions for both of these. This is equal to 1/2 k x squared, where x is the position away from x equals 0, how far away you are from that, plus the kinetic energy, as always, 1/2 m v squared. So wherever you are, you know the total mechanical energy because you figured it out from the amplitude, and you also know what the potential energy is because you know where x is, and so you could find the velocity. So now, just from the amplitude, you also know the velocity at any x. And then you also know the potential energy is equal to this, so you also know you can know the kinetic energy if you know the velocity. So basically what all of this does is this relates all of these quantities, and this relates all of these quantities, and they're all known just by mass and one of these and one of these. So I hope that was helpful, and let us know if you have any questions.